Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. I want to send a quick thanks to our friends at Cloudera for their sponsorship of this series of podcasts from the Strata Data conference, which they present along with O'Reilly Media. Cloudera has long been a supporter of the podcast. In fact, they sponsored the very first episode of TWiML Talk back in 2016. Since that time, Cloudera has continued to invest in and build out its platform, which already securely hosts huge volumes of enterprise data, to provide enterprise customers with a modern environment for machine learning and analytics that works both in the cloud as well as in the data center. In addition, Cloudera Fast Forward Labs provides research and expert guidance that helps enterprises understand the realities of building with AI technologies without needing to hire an in-house research team. To learn more about what the company is up to and how they can help, visit Cloudera's Machine Learning Resource Center at cloudera.com/ml. All right, everyone. I am here with Shioulin Sam. Shioulin is a research engineer with Cloudera Fast Forward Labs. Shioulin, welcome to This Week in Machine Learning and AI.
Thank you. Thank you for having me.
Absolutely. I am really excited about our conversation. We are going to be diving into some of the work that you've done recently exploring learning with limited labeled data. But before we do that, tell us a little bit about your background. How did you get started working in AI?
So my background's actually in electrical engineering and computer science.
Go double E.
Yeah. So after graduation, I worked in the financial industry designing quantitative trading strategies. And then that got a little bit old because I felt like we were using data, but not really for the right reasons or the right thing. Then I kind of stepped back and started to focus more on early stage venture investments, where I mostly looked at women-led companies and try to essentially help them through the whole startup venture fundraising phase. And after that, I realized that I actually really, really love data and missed programming. I miss actually building things. That's how I found my way back into nitty-gritty work and in Fast Forward Labs.
I remember when I finished. Actually, I don't think this was the case for undergrad, but for grad school. Like we were just at the time when the consulting industry was like sucking a lot of people out, and it was a transition from when consulting was taking everyone to when financial services was taking everyone.
Yeah, I think my dissertation was in operations research and operations management. Okay. So a lot of us went into management consulting. Okay. And then the next, I guess, popular choice was finance, specifically the quant stuff. Okay. Yeah. Nice. The OR stuff was one of my favorite classes in grad school. Like I'm trying to remember the name of the software that, God, I would be so dating myself to say that you got the textbook and it was this floppy disk in the back of the book. Yeah. It had like a Puma on it. A Puma. Yeah, it was basically a linear program solver thing. I forget what that thing was called. But that I really enjoyed the whole dynamic and stochastic programming and linear programming and stuff like that. And every once in a while, I get to kind of geek out with folks that took operations research stuff. So you went to the dark side, the financial services path. But now you're back doing research and focusing on data and data science. What exactly do you do at Fast Forward Labs? Cloudera Fast Forward Labs. Cloudera Fast Forward Labs. So at Cloudera Fast Forward Labs, our goal is to bridge the gap between research and industry applications. And one of the things that we do is publish research reports.
And these reports are meant to highlight capabilities within machine learning that we think will become important for the business community within the next 6 months to 2 years from when they're published. So we spend a lot of time focusing on research, focusing on what capability we should actually write about. And we also, as part of that, consult with clients. We are essentially their best friends, best data nerd friends. So we try to help them implement this capability within the corporation, within the enterprise, and then they can always come to us with questions, and that's accomplished through advising hours.
And I've long been a big fan of what you're doing. Hillary was one of my first interviews on the podcast. And last year's Strata, I interviewed Justin Norman, and we talked about the current report at that time, which was federated machine learning. I think in that interview, I referenced that one of my favorites was the report on summarization. I thought that was really cool.
Oh, yeah.
But the most recent report is one that you've worked on, and that's on learning with limited label data. So what motivated that report?
A couple of things. So we see a lot of enterprises sitting on a large amount of data, real-life data that they cannot actually leverage and turn into anything useful. And one of the reasons is that real-life data is very messy and unorganized and unlabeled. But supervised machine learning, for example, require precise labels and a lot of data for you to be able to actually use it. And because of this, what companies end up doing currently is essentially creating labels manually for each one of their data. And that's essentially their attempt to be able to convert the data into anything useful. But that effort is very brute force. It's also not very effective. It's very expensive and doesn't scale very well. So there has to be a better way to do this. And active learning is one way that allows you to learn with limited label data. With active learning, you can actually just smartly select a small set of label data, use that to build a machine learning model. And then that essentially opens up capabilities that you weren't able to do before. You can now build new products that your enterprise can take advantage of using already your existing data.
So one of the things that's always interesting about kind of the approach you take with these reports is that it's very much there's usually something that's happened like in the industry that says, okay, now it's time to do the active learning report, which just sounds like this learning with limited label data is like the active learning report. What's the thing that's happening now that is, is it new advancements in algorithms around active learning or something else?
Mm-hmm. So the report is called Learning with Limited Label Data. And as part of that, we focus on different approaches. We looked at different types of approaches that would help you do that. Active learning was something that we ended up focusing on because it's most mature out of all these other capabilities. We also looked at, for example, weak supervision, meta-learning. That was something that we mentioned in the report, but it's not something that we actually looked into very deeply. So the reason we decided to focus on active learning is because, first of all, it is one way that most enterprises can easily use and take advantage of it and essentially learn from the data. The second reason is that recently there's been a lot of algorithmic improvements in active learning that allows it to be used for deep learning. The classical active learning strategies don't work very well for deep learning, mostly because deep learning is very highly nonlinear and also highly complex. So many of the existing strategies are hard to translate over. And it's not something that you can just easily take and apply in a deep learning setting. The other reason is that deep learning trains in batches. And in active learning, what we're doing is you start with a small set of labeled data. You build a machine learning model using that small set of labeled data. The machine learning model is then used to make predictions on your entire pool of unlabeled data. In the process of making prediction, the model also identifies points that are difficult. And this point is then sent to a human being. The human provides labels for it. This label is then added back to your original smaller labeled data set, and then you iterate this process. So in active learning, you're adding small chunks of newly labeled data, but this small chunk of newly labeled data doesn't really make much impact in a deep learning setting. So recently, there's been just advancement that tackles both of those issues.
Are there different types of active learning? How you describe generally kind of how it works. Are there different types of algorithms? How broad is the field of approaches within under the banner of active learning?
Yeah, at the heart of active learning is a model that is able to identify difficult data points and request labels for it. So how does it actually do that, right? It turns out this model actually relies on strategies, and this strategy selects the difficult data points. So there are classical strategies, and there are strategies that there has been adapted for deep learning. So classical strategies, the easiest one is random sampling. In random sampling, you're really not following a strategy. You're randomly picking data points to get labels for. So this is the simplest possible way. And something slightly more complicated, but something that actually works is uncertainty. So when we say models look for difficult data points, what does that mean? One way to think about that is the models will look for points that it's uncertain about. And then when we get there, then we need to actually quantify what uncertainty means. So there's a slew of strategies that try to quantify uncertainty. And one way is to look at the distance between a particular data point and its decision boundary. These data points that are far from the decision boundaries, you can interpret that as points that the model is very certain about. Any small changes in the decision boundary doesn't really affect the classification of those points. But when the points are very close to the decision boundary, you can think of that as the model being uncertain about these points, because any slight changes in the decision boundary due to model refinement will cause these points to be classified differently. So in margin sampling, for example, we are essentially looking for data points that are very close to the decision boundary and getting labels for those. And once we have those labels, they are then added back to our original labeled data pool and then used to build a better model.
I guess when I think of active learning kind of non-technically, right? Loosely, I think of you kind of run, you train, like as you said, you train your model, you have your model make some predictions, and then when we're doing things like classification, we'll also often see return value that's like the probability, confidence, or the probability with which your model thinks that it's the right classification. Is that probability the same as? Can we use that as part of active learning, or?
Yes, that's in classical active learning strategies that works. You can use the prediction probability as a proxy for how confident the model is, for example. But this way to measure uncertainty for deep neural networks doesn't really work. because deep neural networks are very, very complex, and there are a lot of parameters. So there are times when you could perturb the image using some noise, and you will get an unexpected misclassification. So this is along the lines of the generative adversarial problem. You can perturb an image that goes into a deep neural network and have it misclassify unexpectedly. So for example, you would send an image of a panda with some noise into the deep neural network, and it will classify it as a gibbon, but the prediction probability is actually really high. So although both images look like a panda to a human being. To the network, the one that's perturbed looks like a gibbon, and the deep neural network is very certain of that. So it will say, oh, this is not a panda, this is a gibbon with 99%. So if we use that prediction probability as a gauge of uncertainty in deep neural networks, that doesn't really work. So there are many different ways to essentially look at how to judge uncertainty in deep neural networks. And in our report, we look at 3 major ones. The first one is essentially to use the adversarial approach and to measure what you would like to do is to measure the distance between a data point and the decision boundary, similar to what we do in the classical approaches. But that's not tractable in deep neural networks because the decision boundary is highly nonlinear and you don't really actually know what it looks like. So what ends up happening is we could estimate that distance. For example, we could use the distance between a data point and its next closest a different class object. But that one will only give you a very coarse estimate of the distance that you're looking for. A more creative approach is to use the adversarial approach. So what you try to do is perturb the data points and perturb it such that it switch classes unexpectedly. So when you get a misclassification unexpectedly, the particular data point has switched to a different class, and you use the magnitude of the perturbation to estimate the distance between that data point and the decision boundary. So that is one approach that we mentioned in the report. We also mentioned a fundamentally different way to think about uncertainty for deep neural networks, and that essentially gets into Bayesian neural networks and how to estimate the posterior using dropouts.
Okay. Can you elaborate on that a little
bit?
Sure. You knew that question.
Yeah. So like I said before, if you just look at the prediction probability for deep neural networks, and if you use that to estimate uncertainty, that's very misleading. So we need a different way to think about uncertainty, right? Now, if you think about it from the Bayesian approach, with Bayesian neural networks, what you can do is to actually get the weight distribution of the neural network given the training data. Once you have the probability distribution of the weights, you can then write out mathematically really nicely the probability, the prediction probability of the deep neural network. But that mathematical expression is pretty, but it's not easy to compute. So what you can do then, let me take one step back. It's pretty and it's not easy to compute. And in addition, you actually have to implement a Bayesian neural network in order to get that posterior. That posterior is the probability distribution of the weights.
Okay.
Now, so we don't want to do that, right? So how do you actually estimate the posterior? It turns out you can use dropout as a way to estimate the posterior. And once you have the estimate for the posterior, the whole mathematical formula for the prediction probability simplifies down into something that we can easily compute.
How does dropout give you the weight?
Yeah. So dropout, I think many of us are familiar with dropout as a regularization technique. With dropout, you randomly set some weights connecting to the neurons to be 0 with certain probability, right? And once that weight is set to 0, you have a smaller neural network, but you still train that neural network using the initial training data. So what ends up happening is you have a smaller neural network, you're forcing it to work harder. One way to think about that is also through the workforce analogy. If you have a workforce of 100 people, they perform their jobs, on a regular basis, on a daily basis. But now when the workforce becomes smaller, we are essentially forcing the workforce to do the same amount of job. So everyone can do different types of things. So that's essentially that's what regularization is trying to do. Now, when we use dropout in regular deep neural network training approaches. We train it with dropout turned on, but during inference, we turn off the dropout, right? And then we adjust the weight accordingly. Now, if you think about this, if you leave the dropout turned on during inference, what you're getting essentially is samples of the neural network, right? Every time you run inference, you get a different neural network. So if you run inferences multiple times, you will get multiple different neural networks along with multiple different sets of weights. And you also know with what probability or what likelihood each set of weight will happen.
Why do you have different sets of weights when you're running in inference? I'm imagining that you go through some process of training your model, you create a model, it's a set of weights, you deploy that out somewhere and you're running inference against it.
Right.
I don't think of those weights as changing.
Right, but that's the normal way to use dropout.
Okay.
Right. But if you leave it turned on during inference, what's going to end up happening is you're going to get some neural networks, some weights set to zero with some
I missed
probability.
that. We're leaving dropout turned on during inference.
Yes. And when you do that, you're essentially sampling from the neural network. So you get different neural networks that looks different, that has different weight configurations. And if you do it enough times, what you're going to essentially have is all different sets of weights along with the probability that it will happen. So we're essentially trying to build the posterior, which is the probability distribution of weights over all the training data. So that is an estimate of the posterior, but when you do that, it makes all the computation easy. And then you can actually simplify the expression for prediction probability.
We can rigorously demonstrate that this allows us to estimate the posterior.
Yes,
That's pretty cool.
It's a very cool. This is actually a very cool paper, or outcome of a very cool paper. I think from a year or two ago.
Do you remember the name or authors of the paper?
Yeah, his last name is Gal, G-A-L. First name Yarin, Y-A-R-I-N. It was a pretty big deal at that time.
And is there anything particular about the way we do dropout? Meaning, the dropout parameter, like, is it constrained in any way, or, any particular pattern to the way we do dropout, or doesn't matter?
You just need to essentially drop out each layer of weight, and then you just get a sample of the neural network that way.
Okay.
So that is one way to think about uncertainty in neural network, and that when you couple that into the active learning process, what you would do is to run dropout during inference, run multiple sets of inference, and then each set of inference will give you a prediction probability, and you take the average of that as your estimate of the uncertainty. And then that gets fed into other uncertainty methods like entropy, for example, to figure out, which points should get labeled.
Okay, so you're not taking that estimate directly. You have to then apply it to an entropy-based model or something like that. Can you explain how those work?
Yeah. So entropy, the idea of entropy is that outcomes of uncertain events carry more information when compared to outcomes of events that we are very certain about. So if you think about a coin toss, the maximum entropy for a coin toss is 1. So when does that happen? That happens when we have a fair coin. When you toss a fair coin, you don't know what you're going to get, right? It's the probability is equally likely of you getting a head or a tail. So that's when you get an entropy of 1. Now, when you think of a biased coin, and in the very extreme case, a double-headed coin, that coin toss event has no uncertainty because you know what you're going to get. So the entropy for that is 0. And the entropy for a double tail coin is also 0. So when you use entropy in active learning as a way to quantify uncertainty, what you do is you compute entropy for all your unlabeled data points, and then you select the data points that has the highest entropy to get labels for. And the entropy computation depends on the prediction probability. So in the deep neural network setting, what you would do is you would get the prediction probability using dropouts, And you feed that probability into the entropy approach to get your data points to get labels for.
We've got active learning working for deep learning. Mm-hmm. We've got a set of methods that work. Is this something that your typical kind of enterprise customer can just pull off the shelf and use, or are they building it from scratch? How hard is it to do? You make it sound very easy. I'll just use some Dropout, sprinkle some Entropy over here. How hard or easy is it to actually do in practice? And how robust is it? Is it? It's not actually changing the performance of your network, but the robustness would be in the degree to which it's sample efficient, right?
Yeah. So let me talk about how you would do it first, and then we'll talk about the performance. The active learning approach is a workflow approach. What I mean by that is you have to have a workflow that allows you to first take a small set of label data, build a model with it, use the model along with the active learning strategy to find the difficult data points, and then get labels for those data points. The labels are provided by a human, and then you have to be able to get those labels back and then add them back to your original label data set and then repeat. Mm-hmm. So there are a couple of blocks for this to work. Obviously, you have to be able to build a model, right? Building a machine learning model, I think many of our clients can do. You have to build the model. You also have to be able to implement the selection strategy, and these can just be these are not very hard to implement in real life. It's just a couple lines of Python code, for example. You have to be able to compute entropy. You have to be able to, if you're using a deep neural network, you have to be able to use some deep network appropriate techniques like dropout or ensemble approaches. Once you implement those, what you get at that point is a set of data points that need to be labeled. Now, in the research setting, what usually happens is the person building the model will create the labels for that. But if you were to kind of productionize this, you need maybe more workforce to label this type of data. And the data that we're talking about can either be images or text, because humans can label those. So with active learning, we're kind of limited to use cases where the data comes in the form of text or images. If you're building an application for detecting for medical diagnosis, then you actually need an intelligent workforce to label those images for you. If you're building applications for text, sometimes you can do it yourself. Sometimes you also need to farm it out to somebody else that can do it at a larger scale. Once you have those, you need to be able to get those data point labels back and integrate it into your system easily and quickly. That would allow you to do a second iteration. So those are kind of the building blocks of active learning. The key is to obviously make everything as streamlined as possible. There are a lot of platforms that will connect your data to the workforce that's providing the labels seamlessly. So that part is kind of taken care of. But you just have to be aware that this whole process should be as seamless as possible because you need to iterate.
Okay.
So that in practice, that's how active learning would work. Is there something that active learning is not that good at? Does that affect their performance? That was your second question, right?
Essentially, yeah. How robust is it?
Yeah.
Is it reliable as a technique?
Yeah. So there are a couple of things about active learning that we should always be aware of. First, and in active learning, there's a learner or a model, right? And then there's also the selection strategy. So the learner makes the predictions, the strategy steps in and picks the ones that the learner has the most difficulty with, and then it feeds it back, gets a label and feeds it back. So in general, in any machine learning problem, picking the right type of learner is difficult, but it's made even more difficult under the active learning setting for two reasons. First, you have to pick the learner when you only have a small set of labeled data. Second, the learner is not only used to make predictions, it is used in conjunction with the strategy to help refine it. So the tight feedback loop between the learner and the strategy amplifies the effect of a wrong learner. What generally happens is we advise clients to use maybe not only a single type of learner, use an ensemble of learners of different types, and that would essentially prevent your labeled data pool from being tied to any particular model in general. So that's one thing. A second thing is the impact of these strategies. Some strategies will result in a biased labeled data pool when you compare to other strategies. So we can use a very simple example. In the margin sampling approach, what we're trying to do is to pick data points that's very close to decision boundaries to get labels for. The data points that are far from the decision boundary sometimes are not even used to build the model. So essentially, your model is built using a set of data that's maybe not very representative of your original data pool.
It's not representative in that, by definition, it's data that the model has problems with.
Yes. Yes, because we're only picking data points that the model finds hard, and then we're kind of refining on that set of data points. And those are the data points that we end up getting labels for. So data points that the model is very clear about or very far from the decision boundary, we don't request labels for them, and then we don't use them when we build the supervised machine learning model.
Considering that as like a class of bias, are there obvious downsides to over-indexing on this particular class of bias?
Yeah, so there's a recognition that active learning will result in some kind of bias. But there are certain types of selection strategies that will help with that. The example that I gave was on margin sampling, where we look for data points right around the boundary. But when you do an entropy approach, for example, you don't really get data sets that's as biased, because the entropy approach doesn't just look at the distance. It is a more balanced approach. There are other approaches such as density-based approaches for sample selection. For those approaches, you're only picking from regions where you have dense data. So essentially, you're kind of trying to counter the bias issue, because I just want data where I want to pick data points from regions that I have a lot of other data points around me. So I'm not kind of focusing on weird little pockets of data. Yeah. So our report covers, the basic of active learning. And obviously that is meant to be an introduction to active learning for our clients. And during our advising hours, what we end up doing very often is going down different technical paths for different clients based on their problem and their data.
One of the questions I get all the time is, I have problem X. How much data do I need to collect? Right?
Yes.
Does active learning help me answer that question?
Unfortunately, it does not. But what it does is...
does it even help me answer that question relative to not using active learning?
Yeah, so I'll give you an example. So for all the reports that we do, we also build prototypes that illustrates the capability. And in our prototype for this particular report is a tool that helps you understand the process of active learning and how different selection strategies affect your approaches, and how does it work on different data sets. So we looked at three data sets. We start with a very simple one, the MNIST data set. That is the Hello World data set of machine learning. It's a series of images of handwritten digits from 0 to 9. And then we looked at a slightly more complex data set. It is the Quick Draw data set. It's a series of hand doodles. We looked at 10 categories. The final data set that we looked at is the Caltech data set. It's a series of real-life images of bridges, of animals, for example. And we also picked 10 categories from those. So, and then we also looked at very different types of selection strategies, starting from random strategy to the more complex ones like Dropout and Entropy.
Mm-hmm.
And we use active learning to build a model using all of these data sets. And so for the MNIST data set, if you're familiar with the MNIST data set, the training data actually has 60,000 points, but we only start with 5,000. We build a model using 5,000 data points, and we look at the model performance, and we use different selection strategies to select 1,000 points to get labels for. And then that gets added back to the 5,000, and that starts the next iteration of active learning. So with 5,000 data points, we're able to get accuracy somewhere in the, I think, 92%. And as we increment, I think we did maybe 7 or 8 rounds of active learning, and we were able to get to 98% accuracy. So that's an indirect way to answer your question. What I'm trying to say is you don't need to use 60,000 data points to build your model. You only need, we ended up with is 5,000 plus 8, maybe 12.
Yeah, I think what it is answering is that, active learning isn't going to, produce any results that says, either given my problem or independent of my problem, if I do X kind of active learning, I'm going to require 75% less data or something like that. It's all experimental.
It's experimental.
That you have to.
Yes, it's experimental. But what it's saying is that we know we need a lot of data, so we just kind of brute force create labels for everything. Mm-hmm. But it turns out a lot of these labels are not useful to the model. Right. So we kind of, if you think about these labeling projects for autonomous vehicles, they start at $1 million and go up from there. Mm-hmm. You just label everything and then you hope that it works, right? But when you use active learning in that kind of setting, you realize that, hey, I don't have to label so many images. I only need to label the images that will be helpful for my model. So that obviously brings down the cost, and sometimes it allows us to get to a model faster. Mm-hmm. And more importantly, the model performs almost just as well, at least in the research setting, when you compare it to a model that you would have built using a much larger data set.
How was that in December? I forget. AWS reInvent, they announced a new extension to the SageMaker platform, SageMaker Ground Truth, which incorporates active learning to some extent. There are some other tools out there. The folks behind Spacey, the NLP library, have what is it? Prodigy, yep. Right. Have a library called Prodigy that incorporates active learning. Have you looked at kind of these off-the-shelf solutions, and what have you seen there?
Yeah, so all of our reports come with a landscape chapter. We look at open source. We look at vendors that help with this particular capability. And this is usually very helpful for clients who are thinking of implementing any of these capabilities. Mm-hmm. So as part of that, we looked at Prodigy. We also looked at a lot of labeling providers. Mm-hmm. And the main difference between Prodigy and AWS SageMaker is that Prodigy, at least from when we're playing with it, is more of a complete solution for active learning. And I say that because with Prodigy, you can actually modify any of your selection strategies. I think it comes with uncertainty sampling using Entropy out of the box, but you can essentially link to any selection strategies that you write yourself. You just have to link it in to the Prodigy framework. AWS doesn't have that flexibility.
It's more of kind of a black box type of a solution.
Mm-hmm. Yeah.
Okay.
So that's the main difference.
If I wanted to play with this, what's the quickest way to get started doing it? You said it's only one line of Python code, right?
It's not. It's more than one line. If you're trying to get an intuition for active learning, I would go to our prototype. It's public. It's activelearner.fastforwardlabs.com.
Okay.
And you can kind of play with that. It's a pretty cool visualization of the process of active learning. If you're trying to do it yourself, you can definitely try Prodigy. If not, you can just start building your own model. Once you have the model, all you need to do is to extract out the prediction probability and feed it into a selection strategy. You can use we always say you should start with random as a baseline, and then move up to more difficult strategies and see how they impact your data, because everyone has a different data set, right? It all behaves differently. But because active learning tend to introduce bias or can introduce bias, it's helpful to always start at the base, which is the random sampling, and then go up to maybe a more difficult one, which is the which is the margin sampling, and then go into the entropy approach, and kind of just look at the data that's surfaced, the data points that surface that's asking labels for. You can create labels for those yourself, and then you can feed it back to your model and try iterating it that way.
Having kind of explored this area and learned a bunch about active learning and the landscape, do you kind of see a world where active learning becomes kind of a standard? It's a pretty exotic thing now, right? Like, not everyone is doing it every time because it's just a standard tool that we apply. Mm-hmm. Do you think that over time it becomes a standard tool that is applied in most situations, or does the bias or other downsides exist such that you'll want to be more selective about when you use it?
Mm-hmm. I think it should be a tool that you use every time when you're starting to build a model. When you're trying to get a sense of what works with your data and what doesn't, it's definitely something that you should use. Also because you might be labeled constrained at that point. Mm-hmm. So it's a good starting point. Whether or not it will work as a workflow for all projects, it's hard to say. But the idea is very simple. What it's trying to do is it reduces the amount of labeling that needs to be done, but at the same time doesn't affect model performance. So if you just think of that, I would say that...
Give me two.
I would say that it should be something that's attempted at least in the beginning. And that will also help you discover something about your data that you might not have realized before. It also kind of will help you verify whether a modeling approach will work or not before you label everything. Mm-hmm. But if active learning works, you actually don't have to label everything. You just continue with the process and you just end up labeling a selection of unlabeled data that is the most helpful for the model.
Okay.
And there are many use cases within enterprises. I mentioned for autonomous vehicles, it's super helpful just because the labeling cost is so high and everyone just indiscriminately labeling. Mm-hmm. If you think about text-based examples, companies get, for example, many inquiries from the customers, right? And these inquiries need to be routed to the right departments. But right now, the routing portion is always the bottleneck. We can build a machine learning model to do the routing, but we need labels. Mm-hmm. Now, when you use active learning, it's not as daunting because you don't have to label everything in the beginning. You just start with a small set of labeled data, and then you iterate on that. And then you figure out which ones you have to label. And that will help you relatively quickly come to a model. And then you can, if you want to productionize it, you might then have to label at a larger scale.
Awesome. Well, it sounds like an exciting project. Shioulin, thanks so much for taking the time to share it with us.
You're very welcome.
Awesome. Thank you.
Thank you.
All right, everyone, that's our show for today. If you like what you've heard here, please do us a favor and tell your friends about the show. And if you haven't already hit the subscribe button yourself, make sure to do so you won't miss any of the great episodes we've got in store for you. For more information on any of the shows in our Strata Data series, visit twimlai.com/StrataSF19. Thanks once again to Cloudera for sponsoring this series. Be sure to check them out at cloudera.com/ML. As always, thanks so much for listening, and catch you next time.